Hey guys, new camera, trying this one out. Let's see how it works. The other one was having a little difficulty with the focus, so I don't know, maybe this one will be better. Hey, we're going to do a little lesson on power factor correction. We've been talking about power factor for a little while now, and now we're going to see if we can correct circuits. Before we do that, we should talk about why we bother correcting power factor. Poor power factor comes from having a bunch of inductors in the circuit, right? And who cares? Inductors doesn't make any difference, right? Well, we don't care. You know who cares? The supply authority cares. Whoever it is that's selling us electricity cares. Because if you look at this circuit right here, which is purely inductive, whole bunch of current flowing and no average power, right? And so they've got to supply you this current. It's in your building doing whatever it's doing, a motor or whatever, and nobody's paying for it. Here's a RL series circuit. Here's some average power, right? But must be a bunch of reactive power here too, because part of the power is negative. Okay, and so what happens is, well, first of all, if you are a residential customer, nobody cares. All right, they're going to leave you alone. Most of your loads are going to be resistive anyway. You're going to have a few motors, maybe a furnace motor, and I don't know what, dishwasher and washing machine, all small potatoes, okay? But if you are an industrial or commercial customer, guys, where you have nothing but motor loads, they're going to worry about how many inductors you have in your circuit, or more specifically, they're going to be worrying about what your power factor is, because they don't want to be sending you a bunch of current, creating a bunch of current and sending it down the lines and, all the way to your house from Bruce Nuclear, and nobody's paying for that. All right, and so what they do is they charge you for your true power, okay, because that's what a kilowatt hour meter reads, but they also check your power factor, and if your power factor is worse than 90% or 0.9, they're going to give you the bill for the power, and then they're going to give you a big penalty for having a poor power factor. All right, and so the penalty is big enough that the customer is going to be tempted to want to try to fix it. All right, and that's what their goal is, that you, as a commercial or industrial customer, fix your power factor. Now, how are you going to fix your power factor? Well, you're going to add capacitors in series with your loads in order to do two things, really. It improves your phase angle, gets it closer to 0 degrees, which is what they want. It also reduces the total circuit current, which is what you want. So we're going to learn how to correct the power factor to unity, and unity is the same as 1, right? It's a 0 degree phase angle, or 100% power factor. And we're also going to learn how to correct to 90%, those two kind of. Okay, guys? So this particular question is Unit 3, Handout 5. Okay, and we're going to try it. Now, we've been doing some power factor questions, figuring out the power, true power, reactive power, apparent power, power factor, et cetera, for all different kinds of circuits. When you see a circuit like this, where I've given you the current and the power factor, you should thank your lucky stars, because it means you don't have to try to figure it out. We've been looking at some circuits, and I've said, first thing you need to do is calculate the current in the circuit and then the power factor, and then you can start a power phasor diagram. Well, if I've given you the current and the power factor, and the voltage, then it's your lucky day. All right, because it means you can go straight to a power phasor diagram. Now, we're going to call this uncorrected, okay, because this is a power phasor diagram for this circuit before correction. Now, it looks like we're going to be trying to correct this thing to unity in a minute, but we're not going to worry about the capacitor right now. We're just going to calculate what's going on with this circuit before correction. So here's my rough sketch of a power phasor diagram, okay? And the power is going to sit here, true power, right? VA here, VARs here, and power factor right in this corner here. And it looks like our power factor is 0.65. So we'll stick that in right now. Now, why did I always go on about calculating the current in the circuit? Because if you have the current and the voltage, you can calculate the VA. And don't even think about thinking that the current times the voltage is the true power, okay? Because true power is ER times IR, all right? And these are total values. And don't worry about the verb, okay? Draws, it's a load of, it's, anytime I tell you a current and a voltage, multiply them together. They are going to be total values, E total and I total. Okay, so you don't have to think about it or overthink it. Multiply them together. It'll get you the VA. Looks like it's going to be 250 times 32. Okay, and I'm going to calculate it over here. 250 times 32. Looks like this guy is 8,000 VA. All right, now the power factor is 0.65, which means I can calculate the power. It is going to be the VA times the power factor. All right, so I'm just going to multiply that times 0.65. That was the power factor, you know, before correction, 5,200. That's measured in watts, right, guys? Last thing I'm going to calculate is the VARs. It's going to be 8,000 squared minus 5,200 squared, okay? And I'm going to do that too. 8,000 squared minus 5,200 squared equals root equals. Looks like the reactive power in this circuit is 607.9 VARs. All right, so you want to draw an uncorrected power phasor diagram for every single power factor correction question that you ever encounter. Okay, if you see that it's a power factor correction question, draw a uncorrected power phasor diagram. Usually you can do that by calculating the VA, okay, by multiplying the voltage times the current. Now, if I didn't give you the current, I gave you a circuit, you're going to have to calculate the current yourself, okay? And if I didn't give you the power factor, I gave you a circuit, you're going to have to calculate the power factor yourself, all right? It's unfortunate, but you're going to have to. But in this case, I gave it to you. So we've got a power phasor diagram. Don't even leave this until it's completely full, all right? I've seen students calculate this, and then they move on, okay? Calculate everything. You're going to need it all right, guys? So now it says, now that we've got that, let's see what we're trying to do here. We're correcting this thing to unity. Now, if I want to correct this thing to unity, what I'm trying to do is reduce this phase angle right here to 0 degrees, okay? And what that means is I'm trying to take my VA and bring it all the way down here. Now, how am I going to do that? Well, really, this VARs that we calculated, it's VARs XL, right? This has got a big inductor in it, and so that's all VARs XL. If I add a capacitor that is equal to 6079, I will take care of all that. Now I'm going to draw that, guys, and we're going to draw a corrected power phasor diagram, guys, and you should do it in this order. The first thing you're going to do is draw the power. That power will always be there, okay? There is nothing, you could add capacitors for a month. You are not going to reduce the true power in the circuit. That's going to be there. It's the resistor in this motor, you know, resistance in this motor, and so that's the first thing you're going to draw. The second thing I'm going to draw, guys, is the VARs XL. It's still there also. There's a big inductor in there, okay? And there it is, 6079 VARs. Now, how am I going to take care of all that reactive power with a capacitor? Well, how about I draw my capacitor right there? This is my cap, okay? In other words, it's VARs XC, all right? And I want to make sure I take care of all of it so that when I draw my VA after correction, it is the phasor sum of all three. Here the VA was the phasor sum of the two that were in there, right? Some true power, some reactive power due to the inductor. The VA was the sum of the two. What I've done is added a third, the capacitor, which is VARs XC, and the VA becomes the sum of the three now. So here's my VA. And I don't know what you, but I can calculate, or I can see that that VA is going to be 5,200 volt amps now, all right? And the answer to this question, okay, that cap is equal to 6079 VARs, all right? Now, that is the answer to A right there. Now, it's possible, guys, that you don't need to draw this phasor diagram, this corrected phasor diagram, if you're correcting to unity, because whatever VARs you had due to the inductor will be the size of the capacitor if you're correcting to unity, okay? Because you want to just take care of all that. So it's possible that you could draw this uncorrected phasor diagram, and then, you know, that's going to be your answer. 6079 VARs is going to be the cap. All right, guys? But I want you to see what the drawing looks like after correction here, okay? And so I drew it in here for you. Now, here's the thing. What is the value of line current at unity power factor? Well, in order to calculate the current, I mean, the current before unity was 32 amps, right? To calculate the current after correction, well, the formula that has I total in it is this one right here. Okay, the VA is equal to E total times I total. That means that I total is going to be VA over E total. And the question is, you know, what VA do I use? Well, you use the VA after you've corrected it. And so it is 5200 over the voltage, 250. And I'm going to calculate that here. 5200, whoops, 5200 divided by 250, all right? And it's 20.8 amps. Now, there are some students that think that I total is the, you know, true power over E total, and that's not true. Well, the true power is 5200. Yeah, it's the VA. It's just at unity, the VA and the true power are the same, okay? So the current is always going to be equal to the VA over the voltage. And it just so happens that the VA at unity is equal to your true power. All right, guys? So 20.8, look, 32 amps. What we've done here is we've put the voltage and the current in phase. Okay, this is our phase angle now, 0 degrees, which means if I scope the voltage and the current now, I would get a beautiful sine wave, 250 volts, and 20 amp sine wave, and they would be perfectly in phase, okay? So we've corrected the power factor, we've reduced the phase angle to 0, and we've reduced the total circuit current from 32 to 20.8. All right, guys? So we're going to try correcting to 90% in a minute. Come back for that video.